Hello, good morning. We are going to start once again the merits and the demerits of molecular orbital theory. We have seen that there are certain notable drawbacks which are arised in crystal field theory, which we have already completed. To overcome the drawbacks which are arised in the crystal field theory, a new theory was put forward by Hunt Mulliken in the year 1935 so as to overcome the drawbacks. But in fact, there are again certain drawbacks which are arised in the molecular orbital theory. Just a minute. So, the main drawback which was arised in the crystal field theory that it does not give any idea about the charge transfer, that is the transfer of charge from one d orbital to another d orbital. This particular fact that is overcome in molecular orbital theory because while studying the first MO diagram of TiS263 plus, we have seen that the transition of single electron from non-bonding T2G NMO to EG star molecular orbital that confirms that there is a DD transition of electron, that is transfer or the promotion or the jumping of electron from the non-bonding T2G orbital to the high energy EG orbital, that is sigma star D orbitals. Here we have seen that in this case the surrounding ligands are weak ligands, and because weak ligand field is there, the energy difference between the non-bonding T2G orbitals and the sigma star D, that is EG orbital, that is very small, on account of which the transfer or jumping or promotion of electrons takes place, and promotion of such electron requires very less amount of energy, and hence the electron jumps from non-bonding T2G NMO to EG star molecular orbital, that is sigma star D. So, because of jumping or promotion of this electron, the purple color is observed. This we know. So, another advantage, this is about the DD transition to have a color. Another advantage of molecular orbital theory is that we have seen yesterday two different diagrams of cobalt, one with weak ligand, another is with strong ligand. So, in both these cases, the first complex that we have studied was a paramagnetic because it contains four unpaired electrons. But the case is not true in case of the CONH3 3 plus, where because strong ligands are there, the strong ligand does not permits the unpaired electron to remain unpaired and forces those unpaired electron to pair off. So this is about the magnetic character. So the two merits or the advantages of this molecular orbital theory is that it gives the clear idea about the DD transition of electrons. Secondly, it also gives the detailed explanation about the magnetic properties of different coordination complexes. In this regard, we have seen the first, that is the complex of titanium, where that shows a reduced paramagnetism because of presence of only one unpaired electron. But in COF63 minus, where four unpaired electrons were present, and because of which it is highly paramagnetic. And the next complex that we have completed is a hexaamine cobalt plus 3 ion, where all the electron gets paired up because the surrounding ligand field is strong. So we have seen three different cases by studying the three different MO diagrams. The demerits, if we want to enlist the demerits, then there are around three demerits were observed for molecular orbital theory. The first demerit is that molecular orbital theory explains whether a molecule exists or not. It only gives the Molecule, whether it exists or not, this is strictly depending upon the bond order which we have calculated at our BSc1 level, that is Nb minus Na divided by 2. It is the bond order is nothing but it is half the difference between the total number of electrons present in bonding minus total number of electrons present in antibonding molecular orbital divided by 2. So by using whether the bond order is positive or higher, higher bond order indicates that the molecule is stable and that exists, and if the bond order is zero or negative bond order, that indicates it is a non-existent imaginary molecule. So molecular orbital theory explains whether the molecule exists or not. Second demerit, that this theory seems good for diatomic molecule. That means if a molecule contains only two atoms, that is known as a diatomic molecule. So it seems very good for the diatomic molecules, but it fails to give any idea about the polyatomic molecules where more than two atoms are present, that is known as a polyatomic molecule. So molecular orbital theory fails to give any idea about the polyatomic molecule, but it gives a best explanation for only diatomic molecules. But we are studying a polyatomic molecules where certain ligands are present, the metal atom is present, number of ligands are present. So this theory fails to give any idea about the polyatomic molecules. And third, that the theory does not give any idea about the molecular geometry and the shape of the molecules that we have already studied. So we have not given any idea about, it does not give any idea about the shape or the geometrical shape. So while studying these two diagrams, we have not given any reference of the shape of different molecules. So these are the demerits or disadvantages of this molecular orbital theory. So if we want to conclude regarding this topic, then the main difference between the two MO diagrams, if we want to show, then see this, how yesterday we have seen this diagram. Here we have seen that because the ligand field is a weak ligand field and hence the electrons occupy in high energy sigma star d or Eg star molecular orbitals. This is because the surrounding ligand field is a weak ligand field. But here, in case of the second diagram which we have studied, the 6 electrons coming from the metal, those occupy only in the non-bonding molecular orbital, because this energy gap between the non-bonding and Eg star molecular orbitals, that is very large enough, and because this energy gap is very large, very high amount of energy is required to place the electron in high energy Eg orbitals, but less amount of energy is required to pair the electron. And hence we have written yesterday that when the crystal field splitting delta O value is greater, then the amount of energy required to pair the electron is very less, and hence pairing takes place, which lowers the spin, and hence the complex become diamagnetic. In contrast to this, yesterday we have seen that here the crystal field splitting value, that is delta, is small because weak ligand field is there, and hence because weak ligand field is there, weak ligands interact with the metal d orbitals, very weak or poor interaction is there. On account of this, the energy gap between these two is very small, and hence the amount of energy that is required to pair the electron is very high. And why the amount of energy required to pair it is high? Because the surrounding ligand field is weak, and under the influence of weak ligand field, the weak ligand field does not permit the electrons to pair off, and maximum number of electrons prefer to remain unpaired so as to give paramagnetic nature. So the main difference between these two diagrams, that in when the metal atom cobalt with fluorine, two electrons were present in Eg orbitals, but in the second diagram, these two electrons are forced to pair in the non-bonding molecular orbital. So this is the only difference between the two diagrams. So if we look the two diagrams, you can find that there is only difference of Eg orbitals containing electrons or not. So Eg orbitals are empty because the surrounding ligand field is a strong ligand field, and Eg orbitals occupied by single electrons because the surrounding ligand field is a weak. So we have seen the D6 case where the 6 electrons are distributed. Now the topic that we have studied, that comes to an end. In this topic we have studied In this topic, we have studied the theory that is put forward to study the coordination complexes, how the d orbitals split up into T2g and Eg group of orbitals, that we have studied in terms of crystal field theory. Then we have studied the different shapes of d orbitals upon which the crystal field splitting of d orbitals depends. Then we have studied the basic assumptions of crystal field theory in more details. We have also completed the crystal field splitting of d orbitals of metal in octahedral, tetrahedral and square planar complexes. Now you are very well familiar with the crystal field splitting of d orbitals in case of octahedral, tetrahedral and square planar complexes. We have also seen that some of the students very effectively delivered the seminars on this aspect also. Then we have studied the Jahn-Taylor distortion, where we have seen that if the Eg group of orbitals if are asymmetrically arranged, then the Jahn-Taylor distortion, that is some octahedral complexes, they do display some uneven geometry. So this we have studied while studying the Jahn-Taylor distortion. Then we have studied there are certain factors which are responsible for the crystal field splitting, that is the delta values. So we have enlisted some 4 to 5 factors in this regard. We have also finished the high spin and low spin complexes. The concept of high spin and low spin complex basically depends upon the strength of ligand. So ligand field strength that ensures whether the complex is a high spin or spin free or low spin or spin paired complex. So this we have covered in high spin and low spin complex. Upon this we have also seen one seminar also. Now the crystal field stabilization energy, that is CFSE, we have completed the worksheet on this aspect also. So now you are very well familiar how to calculate the crystal field stabilization energy as in case of octahedral complexes. So it is very easy. During exam, sometimes a case may be given, whether it is a D1, D2 or up to D10 cases. You have to arrive at the crystal field stabilization energies of these different ions. That worksheet you have already submitted. So it is very easy how to calculate the CFSE values. Then we have studied certain limitations of crystal field theory. Then we have started with the molecular orbital theory, the postulates, and in this regard we have completed 3 different MO diagrams containing around 30 atomic and molecular orbitals. So we have drawn around 120 atomic and molecular orbitals in this regard, and we have finished the 3 MO diagrams. So these 3 MO diagrams are very important from the examination point of view. So you should be very well familiar with these MO diagrams. The diagrams are very easy to draw once you remember how to draw the diagram in terms of various atomic and molecular orbitals with regard to the LGOs, with regard to again the notations that is given strictly according to molecular orbital theory. And just now we have finished the merits and demerits of this molecular orbital theory. So the topic metal ligand bonding in transition metal complexes that has come to an end. I will post the notes of this topic very soon on your group. You have to take a printout or whatever possible ways you can make it possible for the purpose of examination. Then we are going to switch over to the next aspect, which is very simple, but don't take it very lightly because this topic contains a lot of chemical reactions. The name of the topic is catalysis. Before the change of the syllabus, the same topic was included at BSc 2 level, but last year, after the syllabus was revised, this topic is again included for BSc Part 3 level. So in this topic, we are going to cover certain aspects. That is, we have to see what is the exact definition of catalyst and the phenomenon that is known as a catalysis. Then we are going to study how the catalytic reactions are classified into two different types, that is a heterogeneous and homogeneous type of catalytic reactions. So this is known as the classification of catalytic reactions. Then we are going to study how the heterogeneous and homogeneous type of catalytic reactions are classified, are different into different types. There are 6 different types, that is positive catalysis, negative catalysis, autocatalysis, then acid base catalysis, induced type of catalysis. So all these types of catalytic reactions that we are going to study by taking some 2 to 3 chemical reactions, and we have to define all these catalytic reactions also. Then in this topic we are going to study what are the different characteristic features which are associated with the catalytic reactions. So these are the catalytic reactions that we have to study. Then we have to study the mechanism of catalytic reaction, how a particular reactions proceed in a particular pathway by using certain theories. In this regard, we are going to study in detail the theories of catalytic reaction. 2 theories were put forward. The first theory is known as intermediate compound formation theory, and second theory that is known as the adsorption theory. And last, we have to see what are the different applications of these catalysts in industrial processes. So that will cover in the industrial applications of catalytic reaction. So I would like to define first of all the word catalyst and the catalytic phenomenon that is known as a catalysis. We know if we want to carry out a particular catalytic reaction, then a catalytic reaction that proceeds, sometimes the catalytic reaction that proceeds with a very high speed, or sometimes the catalytic reaction, though those reactions end up with a very low speed. Certain industries which run on these applications of catalytic reaction, where the quality and the quantity of the product that matters. Every industry that runs on the use of these catalysts. So these industries utilize these substances which speed up the chemical reaction. So if at all the rate of reaction, if it is increased, then the yield of the product that will be also maximum. So nowadays nothing a single industry can run without the use of these catalysts. So the main part of every manufacturing industry is the use of catalysts in one or the other form in under different temperature and the pressure conditions. Suppose for example, if we take for instance the manufacture of sulfuric acid, the sulfuric acid that we use in laboratory, that can be manufactured by using 2 important methods. One method that is known as a contact process, where either platinum or vanadium pentoxide is used as a catalyst. Another method is known as the lead chamber process, where the oxides of nitrogen, that is NO, that is used as a catalyst. In this case, the basic or skeletal reaction to manufacture sulfuric acid is oxidation of sulfur dioxide into sulfur trioxide. So just see the chemical equation for this reaction. Now, for example, just listen carefully, don't write anything. The main or basic equation is a twice SO2 plus O2. Sulfur dioxide is catalytically oxidized into sulfur trioxide. That means sulfur dioxide in presence of atmospheric air, that is converted into sulfur trioxide. It is showing only 10 minutes are left. Now in this case, this is the main or fundamental equation for the manufacture of sulfuric acid. Now in this case, what is our aim? Our aim is to convert sulfur dioxide into sulfur trioxide, but this percentage conversion should be maximum. Now if we carry out this particular reaction merely by sulfur dioxide in presence of atmospheric oxygen, which use sulfur trioxide, this is the normal course of the reaction, but the percentage conversion is very less. Now our aim is to increase the percentage of conversion of sulfur dioxide into sulfur trioxide. Then we have to use certain substances. These substances, they enhance, alter or change or increase the rate of reaction. These substances which are responsible to increase the rate of reaction or the velocity of a reaction or to increase the speed of a reaction, all these substances are known as a catalyst. And those reactions which involves use of such substances which act as a catalyst, this phenomenon is known as a catalysis. So it is actually a Greek word, a catalyst. This is a Greek word that is known as a catalyst, means to speed up. So those substances which are used to speed up a chemical reaction, all substances are known as a catalyst, and the chemical reaction involving the use of such substances is known as a catalysis. So catalysis is a phenomenon, while catalyst is a substance. Either this catalyst may present in solid state, sometimes it may present in terms of in the form of a liquid state, or sometimes it also in the form of a gaseous state. So these catalysts may be in solid, liquid or in gaseous state. So if we take this particular reaction, that is conversion of sulfur dioxide into sulfur trioxide in presence of atmospheric oxygen. In this case, if platinum is used as a catalyst, then the reaction rate is increased. That means before the use of this substance, the percentage conversion is only 2%. In absence of this substance, the percentage of conversion is only 2%. That means whatever quantity of sulfur dioxide we have taken, only 2% of which is utilized in the formation of this sulfur trioxide. Rest being 98% is unused or unconverted. Now, in order to increase the rate of reaction, or in order to increase the speed of a reaction, or in order to alter or in order to change the speed of a chemical reaction, we have to use certain substances. So if platinum, or sometimes nowadays vanadium pentoxide is majority times used, it is used as a best catalyst. So either platinum or vanadium pentoxide is used, then the percentage conversion is about 98% conversion is there. So just in presence of this substance, either platinum or vanadium pentoxide, this reaction rate is increased or the speed of a reaction is increased. So such substances without which the percentage conversion is very less, but in presence of these substances the reaction is brought about. So the peculiarity of all such catalytic reactions is that the substance which is used as a catalyst, this substance can be recovered, this substance which act as a catalyst that can be recovered. That means this same substance can be used for years together. So it is not at all necessary to use for some reaction another uh, catalyst. So the same substance which remains chemically unchanged at the end of a chemical reaction is known as a catalyst. So in simpler terms, we can define the process or the phenomenon of catalysis is that any substance, you have to remember these words, any substance which alters, alter means to change, or any substance which increase, or any substance which increases the speed, or any substance which increases the velocity of a reaction, or any substance which enhance the speed of a chemical reaction and which remains chemically unchanged is known as the catalyst. So this is a simpler form of the definition of catalyst. And the chemical reaction which involves the use of these substances either in solid, liquid or in gaseous state is known as a catalysis. So any chemical reaction, any substance which alters or increases the velocity of a reaction, that substance is known as the catalyst and the phenomenon is known as a catalysis. So this is how the simple definition of catalyst and the catalysis can be shown. So it is in brief, we can say that in absence of either of these substances, the rate of reaction is very low. That means indirectly the percentage conversion is also very less, and hence in order to increase the percentage conversion of this sulfur dioxide into sulfur trioxide in presence of atmospheric oxygen, that is to be increased in the presence of platinum or vanadium pentoxide. So this is known as a catalyst and this phenomenon is known as a catalysis. So only 2 minutes are left. I would like to mention certain I would like to give you certain instructions regarding our tomorrow